Okay, let's start. And so since we don't know each other, but if I ask you all the names, I will forget in 2 seconds, okay? So, I mean, just with calm, every time you start asking questions, then I will ask your name, and then it will take some time, but I will remember. So, today we are going to discuss about a new concept in quantum mechanics, which goes under the name of density matrix. Did you hear about this? Just here, or you know about density matrix?
Just here, yes.
Okay, so this is totally useless, okay? So now you have to do a step forward and understand what is a density matrix, okay? So far, you learned that in order to describe a quantum system, then, so you use vectors in Hilbert space, okay? So you just, if I give you a quantum state of a wave function in some coordinate representation, then this is a description of certain state of a quantum system, right? If I say yes, if I ask you a question, you say yes or no.
Yeah.
Very good. Is it clear over there?
Yes.
Now, a quantum state or a wave function, a quantum wave, I mean, let's use the bracket notation, okay? If I write this, then I'm just saying that I have a system, I don't know, electrons, hydrogen atoms, spins, whatever. And this quantum state contains all the description of the quantum state, say, the maximum information that I can extract compatible with quantum mechanics, okay? So you know that if you have 2 non-commuting observables, then you cannot determine with absolute precision, right, the corresponding eigenvalues, right? Because there are no common eigenvalue. Okay? So if you take the states, this can give you essentially all the information you are able to get from your system. So a state obeys a dynamical equation, which is the Schrödinger equation. Okay? So for instance, you prepare a state in some ways, then the system is subject to some Hamiltonian. Then if I ask you, okay, I would like to know what is the state after a time t, then you have to solve the Schrödinger equation with the given Hamiltonian, considering the initial state as initial condition, and then you see how the system evolves. Okay? Now, quantum mechanics provides, let's say, some kind of ignorance. Okay? So if I write the wave function of a particle, so a wave, okay, plane wave, then you may determine the value of the momentum of the particle, but then you have no information about the position. Okay? This is one example, but I can give you infinite examples. So I will call this, let's say, ignorance that you have on the system, which is related to quantum mechanics. So it's not like in classical system that you can determine all possible properties of a certain classical particle. In quantum mechanics, there is a limited, this is limited by, let's say, this quantum ignorance. But within this ignorance determined by the laws of quantum mechanics, the state contains all possible information you can extract. Now, do you know what is a spin? I don't hear it. No, nobody. So they don't hear. Okay. So if you see, once they see you in, they are not going to see you on YouTube. They think that I am talking along like a crazy guy just entering an empty room and. Okay. Okay. So do you know about Pauli matrices?
Yes.
Perfect. Do you know about Stern-Gerlach experiment?
Yes.
Excellent. The best class I ever had. Okay. So I would like to start with the Stern-Gerlach experiment to tell you that there are cases in which, in addition to, let's say, this type of quantum ignorance, I may have additional ignorance that comes from other sources. Let's call it classical. Okay? I will consider a very, let's say, I think a simple situation which is useless. Okay? So don't try to give a real meaning to this, but just to, I think it's simple enough to tell you that sometimes there are certain situations in which using a quantum state is not a good description of the experiment of the situation that I would like to consider. And this is the topic of this lecture. I would like to explain you that there are several cases, very important examples, in which your quantum system cannot be described by a state. So we need a different object to describe the system. Okay? This object is called density matrix. This object reduced in appropriate limit to a state, but encodes a more general class of possible experiments. Okay? Now, so everybody said that you know the Stern-Gerlach. Okay, so how does it work? So next time you will sit down on the last row, right? And then I will just address. Okay, so what is your name? Edward. Okay.
So it works by ejecting atoms from a source and then letting them pass through a magnetic field.
Very good. So suppose that these atoms are just spin up and down, then pass through a magnetic field, some gradient, and
the magnetic field deflects them in opposite directions.
Very good. Okay? So suppose that the magnetic field is aligned along z direction. Then, say, there is one beam that goes up, one beam that goes down. then what can I say about the beam that goes up and down? What is the state? So just imagine that if I put a screen, I get two spots, okay?
The one that goes up is spin, the ones with spin up, and the one that goes down.
Yeah, very good. But then you have to say, so this is correct, but then you have to say it's spin up along
the Z direction.
the Z direction. Okay, this is important. Now, this is if you put a screen, right? Now, suppose that instead of putting a screen, you just look at the beam which goes up, okay? So it's a given direction along Z. And then you put a magnetic field along X direction. Any direction, which is not Z. Well, what happens if you put the screen after the second?
I will get again two spots with.
Very good. Because you are entering with all spin up along Z. Okay, but then I will select the magnetic field will select along the X direction. Okay, so and then if you write down the state Z in terms of the X eigenvalues, then you get plus and minus, right? So you see, this is a type of, this is what I call quantum ignorance. So if you prepare a system along Z, then you select or you measure along X, then you will see two spots. Okay? Now, okay, that's perfect. Now, suppose that I would like to do the following experiment. Again, the experiment itself is useless, okay? But I want to do it. I have a coin, okay? Then I just throw a coin. We cannot do anything. So I just throw the coin, okay? And I have a head of tails. Depending on what is the output of the coin, then I just change the orientation of magnetic field, and I put it either and I put the orientation of the magnetic field around along Z or along X. Okay, this is the experiment. You can imagine that I send one atom at a time. So each time I just do coin tossing, and he just tilt the magnetic field. And then I want to get, I would like to describe the state of the system. Okay? Yes?
We have only one device, right? Not two devices.
One device for the moment. So I'm just changing the preparation. Okay, so the preparation is not fixed, but it just depends on just coin tossing. Now, can you describe the quantum state of the system? So eventually what you would like to do is first, if you want to analyze the outcome of experiments, then what you have to do is theoretically, I mean, you can do the experiments, one second. You can do the experiments and then you see some spots, okay? Then if you want to do, you want to analyze the experiments, then can you write a quantum state? Yes?
Should I come or should I just describe what I find?
No, just describe.
Okay, so I have one half of probability going up and down, and then one half of going x and y plus or minus, sorry, x plus or minus. And each one of these have a normalization of 1 square root 2. So I have 1 over 2 square root 2 of the 4 of them.
Very good. You're going very fast, so let's slow down. So she gave a suggestion, which I think is correct. Okay? Now, my next question is that in the, what is your name?
Position of them.
Ahmed. Ahmed with an E, Ahmed.
Amel.
With A. Amel.
Amel, okay. Edward Amel, I mean, my hard disk is rapidly saturating. Now, my question to everybody, okay, including Amel. In the description that she gave, did she use the fact that the quantum system is described by a quantum state? So if I want to translate what she said, can I write a quantum state associated with this description? So is the question clear? Is this question clear? Yes. Now, what is the answer?
Yes.
I think yes.
Yes. No.
It's like mixing up classical and quantum
Yeah.
probabilities. So
The reason is that what Amel said correctly was, okay, let's start with probability 1/2, I will get up and down. With probability 1/2, I get plus and minus, whatever, it does not really matter. She just started correctly saying with probability 1/2. Now, how can I write this, what she said in words, as a quantum state?
it should be 1/4 spin up in the z direction, 1/4. No, 1/2.
So,
One was square root of
so for a record, I'm going to write wrong things, okay? So, I would like to try, I mean, my question is, so for instance, just to clear what I want to say, if I tell you, I prepare a spin in a superposition of up and down with amplitude 1/√2 and 1/√2. Can I write the state? Yes. I write something like up plus down. Okay? So, I tell you how I prepare a state, and then I know how to write the corresponding using brackets. Now, I would like to understand if what Amel said can be written as a quantum state of some sort. Now, the most general quantum state of a spin, do you agree with me, can be written as alpha up plus beta down, with alpha square modulus square plus beta modulus square is equal to 1. Now, the experiment I designed with the coin can be translated in some values of alpha and beta.
Yes, but it is not 2 square root 2.
Yes, tell me what is. It's something, okay? It's enough for the moment. I don't want to know the numbers, okay? But you say, yes, I can do it. It is just that I have to change alpha and beta. I have to put some other coefficients, okay? This is what you are saying. But then I have a problem. If I change, suppose that I found these coefficients, okay? So we sit down for a bit and she tells me, okay, you have to put 2 over whatever and here something else. Then I just see that I can have, for instance, I can design some other experiment to do some interference between these two terms. right? Because I have a superposition and I can do some interference. But,
Sorry, by superposition we mean that we'll have superposition of 4 states. 2 of them are in the
yeah,
z up, z down, and x up.
but you see, when you have a spin 1/2, that's why I chose this experiment. If you have a spin 1/2, any superposition can be reduced to alpha up plus beta down, when alpha and beta are complex numbers obeying this, up to a global phase that we know.
But by writing up, we mean up in terms
So I
of-
chose, yes, I chose a basis, and you're right, I have to be more, I just choose this basis. Okay, I can change another, I can take another basis and the state will be rotated, so this alpha, not the state, this alpha and beta will change, but at the end, the most, do you agree with me that the most generic state that you know so far can be written in this way? Hmm?
Yeah.
So, when I ask you, if I throw the coin, can I write it as a state? And they say yes. The only thing I have to modify is alpha and beta.
Sorry,
Yes.
but shouldn't be say before because we have possibility of z and possibility of x?
Yes, but since you can write, yeah, so let's do this way. So for instance, I just write alpha up z plus beta down z plus gamma up along x. This is what you're saying, plus delta down along x, right? But then you know that up x is equal to 1 over square root of up z plus down z. Right? Is this clear? Yeah. And you know that down z is 1 over square root of 2 of up z minus down z. Right? So if I take this to definition, put it here, this will become something alpha tilde up z plus beta tilde. Okay?
But shouldn't...
No, just a moment. First, tell me if you agree with what I did.
Yes.
So the space, the Hilbert space associated with the spin 1/2 is two-dimensional. So the basis is this one. Is one of the possible bases. Okay?
Yeah.
So, what you said, so you see that what she's proposing, okay? I think this is, this is the heart of the discussion, okay? So that's why we are spending some time. So, she's proposing that I can have a state, let's say, I just call it this, say 0, and this phi 0, okay? I'm considering a generic case. And the coin tossing, so when I do the coin tossing, I just say, if I get head, I will prepare the state psi 0. If I get tail, I will prepare the state phi 0. Okay, now we can forget about the Stern-Gerlach. I think we can put the discussion on a bit more general terms. Okay? Now, then I ask you, good, if I do this way, is the state that I'm preparing psi 0 plus phi 0 with some normalization, okay?
The question is either the state I'm preparing is the linear combination of both two?
Yes.
No, it shouldn't.
Yes, but this is what we are discussing. Okay? So the proposal that some of you said is that, well, if with the coin tossing I just have either say 0 or phi 0, then the state that I'm preparing is just this, the sum. Okay? This is a proposal. I mean,
Yeah.
we should understand if this is correct or not. Okay? So there are several things which I would like to point out. Now, you know that in quantum mechanics, phases are important, right? So if I put here any phase here, the state will change. Okay? Let's call it gamma or something. Okay? But then in this coin tossing, there is no phase relation that it's just probabilities. Okay? Then you see that there might be an issue. When I do the coin tossing, there is an additional ignorance that I'm putting in the preparation, which has nothing to do with quantum mechanics. This is just related to the fact that I'm just taking a coin and just tossing. Okay? Is this now clear or not? Huh? Is this clear?
Do we assume that the coin is not biased?
Now, for the moment, yes. We have enough problems with unbiased coins. Okay? So if the coin is biased, then if the coin is biased, then what we have to modify is that the probabilities. Okay? What I would like to discuss, so for the moment, is not to find a solution, but just try to convince you that when I have superposition of states, this is related, may be related to, some quantum mechanical ignorance. If I have coin tossing, this is nothing to do with a state. Okay? It's just related to something that is not known in quantum mechanics. Let me see if I can give you.
Can I ask something?
Yes.
So what you are saying is our classical ignorance doesn't change or increase our quantum ignorance.
Exactly. It's totally independent. So let me give you. So I would like to use again this idea to see if. So suppose that I prepare my state with the coin tossing, okay, with 50% up and 50% down, okay. Now, if I put my magnetic field, so when I say up and down, I'm referring to the z direction, okay? So if I don't specify, it's always z. So I just do the following. So I just prepare with 50% up, 50% down along Z, and I put a magnetic field along Z. Okay? What do I get? I get two spots. Okay? And the two spots are,
The spin up and spin down.
yes, the probability, I mean the fraction.
Yes.
Huh? The fractions are?
1/2, 1/2.
No, the fraction are 1/2 and 1/2. So half of the, right? Half of the
Spins go up. half.
spins, about, the one that I prepare up, they go up. The one I prepare down, they go down. And so half. I mean, if it's unbiased, it's 50-50. If the cone is biased, then I have some unbalance. Okay. Now I'm trying to use the initial proposal. Okay. Then I say, okay, I have to prepare a state up plus down. Okay? So this is not, we still don't know if this is correct. I'm just saying that we just do the following. Okay? I just use up plus down with a square root. Okay? Then I put the magnetic field along Z. My question is, what do I get? If I prepare the state like this, so if I assume that the initial state is up plus down over square root of 2.
And the magnetic field is along Z.
Along the Z.
We'll get two spots.
We get two spots with
1/2.
1/2, 1/2. So in this particular case, the proposal of saying the coin tossing is just the state up plus down divided by square root of 2 is just gives me the right result. Okay? There is a third situation in which I prepare the state in up along x. Up along x is just up plus down, which would correspond to the second case. Your faces don't look good to me. Okay, so let's start again. I'm looking for So I would like to consider three different situations. Okay? 1, 2, 3. The one preparation, okay? Preparation is coin tossing okay? And then I know, say, P up is 1/2 and P down is 1/2. Okay? The second situation I would like to consider is, let's call it I call it proposal for description of coin tossing. So I would like to take the initial suggestion that when I have a coin tossing, the state that I prepared is up plus down. Okay? Which is your proposal? Huh? Is this now clear or?
So, because when I do coin tossing, I have two possibilities, right? Two probabilities. Yeah, what is the other probability? Then it is.
This is my question. That I'm trying to convince you that there is no way in which I can write a state for this type of preparation. If you are convinced, then it's fine. I'm trying to do this because you don't look convinced. My claim is, if I prepare the state with a coin, then there is no way I can invent any state which describes this type of preparation. Okay? Now, if you tell me there should be some quantum state for this type of preparation, the only thing I can imagine is a superposition. Okay? And since I have 50%, 50%, this is a good candidate. I can take any other thing. Okay? The third example is, instead of preparing with the coin tossing, I prepare just with the two, I just generate this state by passing through a magnetic field along X, and I just took one of the two spots. In this case, I know that the state I prepare is just up plus down square root of 2. This is X preparation, I call it. Okay? And this I put the question mark. Is this clear now?
Just to make it
Super clear.
super clear for me. In the second case, we are tossing a coin. So, for example, if it's if it will be heads, then we'll.
No, this I don't know. So I want to make this is important. The second case is a guess.
No, just.
So the preparation in both cases is the same. Okay?
Yeah, I don't get it.
Okay. So let's start again. I'm very happy that you are asking questions, okay? So I want to consider two types of experiments. 1 and 3. Forget about 2. Okay? 1 is the coin tossing. The other one, I prepare all the state, all the atoms along X direction, so it's up plus down. Now, question. So, in this case, we all agree that this is the initial state.
Yeah.
Okay? So then if I put another magnet in any direction, then you can tell me what are the probabilities to get atoms in one spot or another, right? You can do everything here. And you will get the probabilities like some trigonometric function of the angle between this X and the direction of the second magnetic field. Okay? So we all know, we know everything about this, so I don't want to solve it.
So we prepared the system in that state without any Stern-Gerlach and.
We prepare the system in this state.
Yeah.
So if you ask me how do I prepare it, the simplest thing is to put a Stern-Gerlach along X, so I will get two spots. I just take one of the two, I forget about the others, and the one of the two spots will be as the initial state for a second Stern-Gerlach.
And on the second Stern-Gerlach, at that time we'll start the coin flipping.
No coin tossing here. No coin tossing. Okay? So in the second Stern-Gerlach, I can put the magnet in any direction. And if I ask you the probabilities to get the fraction of atoms in the two spots, you will find everything. Okay? I'm pretty sure. The only thing you have to get this cosine and sine. Okay? Fine? So here you know everything. Here I'm doing something different. I'm just coin tossing. Okay? It is clear what I'm doing. Now, what we don't know yet is, can I write, so Amel gave us in words what should happen, okay? Now my question is, can we write down what she described as a state and then compute the probabilities according to the rule of quantum mechanics. And so the answer is yes or no. And if yes, what is the state? If it's no, there is no state. Is it clear now? Okay? So, when I asked this question at the beginning, the courageous guys said, yes, we can write as a state, a quantum state, psi. Do I recall correctly?
Yeah.
Is it? Huh? Okay. Don't be scared. It's good to give wrong answer because don't worry. I mean, okay. No, at the exams I will not say it's good to give wrong answer. For the moment, yes, it's okay. Okay. So now, look, I trust you. I trust you. So I would like to try to understand what is this psi. Okay. Now, do you agree that the most general psi I can write is just alpha up plus beta down?
Yes.
Okay, there's nothing else I can do. Okay? Okay? Good. So, since, let's say, this is a question mark, okay? We don't know if this is correct. I'm trying to see if it makes sense for you. Huh? So, let's start this with this hypothesis. Now, since the coin tossing is balanced, okay, this 1/2, 1/2, there is no reason to think that this alpha and beta modula are different. Okay? So I can take 1 over square root of 2 and 1 over square root of 2. It's a good option. And I put a face. And I still have a question mark. Okay? Good. Now, this is a working proposal, okay? Now, let's analyze this working proposal. I consider this coin tossing, okay? So, in words, I just say I prepare 1/2 up and 1/2 down. Huh? Right? Now, if I put a magnet along Z, the two spots will have a fraction of 1/2. Okay? Because I prepare 1/2 of the spins up, 1/2 of the spins down. I will expect that so I will have 1/2 of the.
Yes, but if in the initial condition,
No, this is the initial condition.
this is the.
No, for the moment I'm
this is the
considering.
proposed.
No, just a moment. This is proposed. Now, first I want to analyze. I'm following the discussion of Amal just in words. Okay? So what I would like to convince you is that your analysis is correct, but this cannot be framed using states. This is my goal. Okay? So what I'm trying to do is that first I want to compute probabilities with this reasoning. And then, since I know the rules of quantum mechanics, I will reuse this and show you that you get the wrong result. Okay? So, now first I analyze this probability description. I prepare up 1/2 and down 1/2. Magnet along Z
You get 2 spots.
You get 2 spots and the weight is
1/2,
50-50, right? 1/2, right?
Yes.
Then I do something else. I just put the magnetic field along X.
Yeah.
I will always get 2 spots.
Yeah.
Now, compute the probabilities. So, what are these 2 probabilities? With X.
There is still 1/2.
They're still 1/2, because you take all the up is they split and they go
Left,
right, and you get
Yeah.
25-25. Then the down goes 25-25, but at the end you get 50-50. Okay? Then you take any angle you want. The 2 spots will have a weight
50-50.
50-50, okay? Now, we agree on this. Very good. So, let's see if this hypothetical state gives me the right answer. Huh? So, let me consider for the moment the simple case in which I put phi equals 0. But you will see that it's very simple to generalize. Now, I put the magnetic field along Z. What do I get using this state? 2 spots. I mean, I always have 2 spots, so there's no way I can get more or less than 2. I get 2 spots, and the weights are 1/2. Fantastic. So you see, but that's great, because I get the right answer. Now I put the magnetic field along X. How many spots I get? How many spots I get?
You don't get any spots.
So you found an upper and lower bound to the correct answer. So you said 2, then you said 0. Now 2 is the upper bound and 0 is the lower bound. What is the correct answer?
1.
Why you get 1? Do you get 1 because we saw that this is just up along X.
Yeah.
So if you put the magnetic field along X, then it's like having prepared all the spin up along X. So all the spin will deviate in one direction. So you will get, you only get 1 spot. Do you see?
Yes and no.
Okay, this is classical quantum ignorance. Why? So tell me, what is a yes? Let's start with...
The yes is because we have plus sign, so we know it is up on x-axis.
Yeah, so you had minus, you will get 1 spot on the other side.
But that means when we started, it was not... Oh, we started with probability half, but then we choose one of them, which is this one. Is it like this?
Can you repeat? I did not understand.
Because at first we were tossing coin, and we had half probability, which should give us both the plus and negative, right? Should give us...
Yeah, but this is exactly the point. The question I would like to convince you that this is not the right description of this coin tossing.
Okay.
This is my claim.
Yeah.
Okay? So this is what I want to say. So you solved the problem of coin tossing perfectly. Right? And so when I say don't write states, but just tell me what happened, you just use your knowledge of probability theory. Just tell me that any direction you put the magnet, you will always get 1, 1/2. Huh? Then the next step is that, look, very good. So far in the course, in all your courses in quantum mechanics, you learn that to describe a system, a quantum system, you have to define a state. Then the question, I think the legitimate question is that, is this coin tossing, is it possible to describe this coin tossing by a state? this is the question, okay? And then we saw together that, I mean, I just gave you one example, but you can convince that whatever you take, you always get the wrong answer.
So this way it means that we are always preparing the state in the spin up along x direction.
Yeah, so you can take any state you put here, will just describe some eigenvalue in some angle, okay? So we took for simplicity the x, but whatever you can imagine. So then if you put a magnetic field, then the probabilities will depend on angle.
Yeah.
And this is crucial because here there is a superposition, while here we are just describing with probability, which have nothing to do with the preparation of state.
So
But what we should have is plus and or minus in both of these up and down, no?
What?
Because we
No, can you repeat?
just write plus and minus in front of 1 over square root for both of them.
So what do you want to write?
At the first I should have plus or minus.
So 10 plus, did you say plus?
No, plus or minus. We have four.
Right, but then you are, okay, this is a suggestion, just asking and then I will answer. What is your question?
my point was that, of course, the result shows that writing this wave function, this state is wrong because the system is not in either up state or down state. It's not in the combination. When we toss the coin, it's either spin up or
Precisely.
spin down.
Okay, so you are hitting the point.
Yeah.
So then I follow the suggestion. Okay, psi is plus minus up. Okay. And then, yeah?
Plus minus also.
Very good. Is this a quantum state?
Yes, it's.
No. I never saw any plus minus state.
You take out
So-
plus minus in front.
No, but that's the question. So, look, is this a quantum state?
These are 4 quantum states.
Very good. So probably there are 2 because these are either with the same sign or with the opposite sign. But it's because the overall phase does not matter. So what really counts is that either this situation or this situation, okay?
Relative signs.
Relative signs count, which is okay. So let's write it this way. Okay, is this one state? No, these are 2 states. Okay? But then you see that I have a problem because so far we learned that I can assign to a quantum system a quantum state. Now you are inventing a new quantum mechanics in which you are assigning 2 states to a quantum system.
Yeah.
Okay? Now, the intuition is good in the sense you are getting to the point that there is some classical ignorance that cannot be encoded in the state. I should put an extra ingredient. Okay? As I should take these 2 states, okay? But then I should find a consistent way to describe exactly what I mean by having 2 states. Okay? So I would like to find, and are you with me? So I have to find a way to include the fact that the system can be with some probability P1 in one state and with some probability P2 in 2 states. Okay?
But,
So for it,
but it cannot be in both at the same time.
for the moment, let's consider this situation. Then we will complicate our life. Okay? Because, and so something else I can try to do is that I just write those two states, and then I have to say what is this object. How does it evolve? What does it mean that I compute averages? This type of things. Okay? So I think you are on the right track. What I'm going to do is, it's already 10 past 12. Yes. Okay. I have to find the right mathematical object which encodes all the things we need. Okay, you just saw that there are certain cases in which I have to, it's not that I have a quantum state, I have a system which can be in one state with some probability, in another state with another probability. Okay? So I have to find the formalism which allows me to describe this. Okay? This probability, for the moment, we will generalize this. But for the moment, this probability is just classical. It's for instance, in the preparation. Okay? By the way, did you study thermodynamics? Yes. Did you study statistical mechanics?
We are still studying.
Huh?
We are still studying statistical mechanics.
Okay, we never stop studying.
Yes.
We will study statistical mechanics. Okay. Did you see that to describe a system, you just give a probability that the system is in a given state?
Yeah.
And the probability is e to the minus beta en.
Yeah.
Okay? So this is another example in which you're not saying the system is in a given quantum state. Okay? You're just saying, look, with some probability e to the minus beta E1, it will be in the state psi 1. With e to the minus beta E2 will be in the state psi 2. Okay? This is another example in which there is an extra information, so an extra ignorance which does not come from quantum mechanics, comes from other sources. In thermodynamics, in statistical mechanics, comes from the fact that your system interacts with some external environment, so the energy can fluctuate. So you cannot say it has a given energy or another given energy. Okay? Now, for all those cases and more, we have to introduce density matrices. So, for the moment I consider just the same case as before and show you how to write the density matrix. Okay? So this is a quantum state. Suppose that the system is described by a state psi. Okay? Now, an equivalent way to describe the quantum state. So now I'm considering this case, okay? Then I will show you that how to generalize. But for the moment, you learn how to use to define the quantum state, okay? I can associate an operator. So it's an operator, rho, which is defined like psi. This is the density matrix associated with the state psi. Okay? as far as this description, for pure state, for those cases that you learned so far, using states or density matrix is completely equivalent. How do I see this? So for instance, if I tell you I would like to calculate the average of a given operator observable on the state side, how I do it with state? So if I have here the operator O, and I want to know what is the average value of O on the state side, what should I compute?
Bracket between.
So I should compute, so the average O is just psi O psi. Okay? In this formalism, O is nothing else than the trace of rho O. Is this clear? Don't say yes. No. You do know what is a trace?
Yes. The sum of the
Yes. So I have to do the trace over psi O. Okay? This is the operator, right? And this is the density matrix. Now I can always choose a representation such that one element of the basis is psi and all the other elements are orthogonal to psi. So this is equal to sum, let's say, so to psi O psi, okay, plus the sum over all the other orthogonal elements, psi dagger psi O so you say yes.
Yeah.
You say no.
Not as in I disagree, I don't see it.
Which is a no? You say yes or no? I don't know. You say no. No. Let's use a binary code, yes or no. Okay? Yes or no? Yes. No. I said yes or no. Choose. No.
Yes.
Flip the coin.
Flip the coin. Okay. So how do you do the trace? You said you sum over
All possible.
very good. So a diagonal element of what?
Which are satisfied with the
So let's try to decompose this diagonal elements trace. Okay? So I choose a basis. Okay? Then, so this is what you are doing mentally. I choose a basis. Then I write down the matrix in this basis. And then I took the diagonal elements and I sum. Right? Very good. So, this means that, for instance, if you have a basis phi n, okay? So it's just given basis. When n goes from 1 to capital N, this is a basis. Okay? Right? Now, when I say I want to do the trace of operator O, this is equal to summing all the diagonal elements. So this means sum over n of phi n O phi n. Right? Very good. So the trace over O times M. This is equal to
Double sum.
no, just the simple sum for the
Yeah.
moment. Then the simple sum is sum over n of
Psi n or m psi n.
very good phi. This is phi n o m phi n, right? Very good. Now I have some Hilbert space and I choose a basis. Okay? Now I choose the basis. So suppose that the space is given by f is n-dimensional, okay? I choose the basis such that phi 1 correspond to psi. Okay? So I took the state. So that all the phi I with I larger than 1, they are orthogonal to psi because it's a basis. Okay? Very good. So this is rho, okay? So this I write as phi 1 rho O phi 1 plus sum n bigger than 1 phi n rho O phi n. Okay? Now let's list this. This is phi 1 psi O phi 1. So phi 1 psi is 1. And this is nothing else than psi. Okay? So this is exactly what I wrote here. Now all these terms, this one, have phi n psi times, what is this? 0. Okay? So if I use the state O, the average is given by this. If I introduce the operator rho, the average is given by the trace over rho times O. Now you cannot say no. No, you are allowed to say no. But now, is this clear or not? No. Is this clear or not? So what is not clear? Don't think to the pen.
Maybe I have to think about it.
Okay, think about it and tomorrow I will ask you. So what I want to tell you that we'll come back tomorrow, don't worry, okay? So look, you are used to this strange symbol, and now since you have been seeing this strange symbol for years, then it's okay. But if I use this other strange symbol, it's as well, it's okay again, okay? It's just that you get used to. The only thing I want to convince you is that if you use this projector, this state, you have exactly the same description as using state, okay? So I just say, look, what is the state is psi. You can associate an operator which is psi. So you want to describe averages, okay? Averages, either you do psi or psi, but if I give you the density matrix, you have to take the trace of rho times O. It's a rule, okay? Something else. So if I tell you, what is the probability that the state psi that the system given by described by psi is in phi. How do you compute? Or let's do it. The probability that the system is up. Say, suppose it's a spin. What should I do? Huh?
Sandwich the spin up operator.
Very good. So you have to do up psi square. Okay? Or whatever. If it's in any phi, it's just this. Okay? Now, how do I do it with the rho? The probability of being in phi is nothing else than phi rho phi. Because if you substitute this rho here, then you get phi psi times psi phi, which is phi psi modulus squared. Okay? So I know also the probability. So in the last 5 minutes, so what is the time evolution of the state psi? It's described by the Schrödinger equation. So what is the Schrödinger equation? Just by heart.
Phi h ddt.
Psi is equal to h psi, right? Very good. So I would like to know how rho evolves in time, right? So if I start with the state psi, now if you start with psi, what is can you write the evolution of psi at a later time with the unitary evolution? Huh?
Apply the time evolution.
Eh?
The time evolution of program.
Yeah, which is, suppose that it's time independent Hamiltonian.
The exponent.
So this will be something like e to the minus I over h bar psi. Okay? Now the same is here. So I have e to the minus I h bar t, h t over h bar, and here I have a complex conjugate. Okay? Which means that if at rho at time 0 the system is in psi, the rho at time t will be just psi of t, psi of t. Okay? I already told you, if I have a state psi of t, the density matrix is psi of t, psi of t. But since I know that psi of t is this one, then I can write the density matrix also in this way. Now, what happens if I take the time derivative of rho? Okay? So the time derivative of rho is taking the time derivative of h, of this, nothing, plus the rest. You just do it. And then you find that this is equal to minus the commutator of h rho. This is like the Schrödinger equation. It's not called Schrödinger equation. Okay? So this is the differential equation that is obeyed by the density matrix. Try to do it yourself. Okay? It's not difficult.
I over h.
Huh? Yes, I always keep putting h bar to 0. To 1, so I forget. Yes. Okay? So, something which I would like to stress to confuse you even more. Rho, the density matrix, is the only operator that evolves in time in the Schrödinger representation. Remember, so you know that operators in the Schrödinger, you know what is the Schrödinger-Heisenberg representation, right? So you know that in the Schrödinger representation, operators do not evolve in time, okay, are states. Now rho, it's an operator, but it's weird because it's an operator which describes the state. Okay? So this is similar to what you saw about the Heisenberg evolution of the operators, but the meaning is different. This is an equation which describes how states evolve. Now, you can ask me, look, why do you bother us with all this? It's a legitimate question. So far, indeed, I show you that I can use this cat, or I can use this, and it's exactly equivalent. It is exactly equivalent. Okay? Tomorrow, we are going to see that when I have this coin tossing, and I keep insisting using this psi, I go nowhere. But the coin tossing, using this density matrix, is just in one shot. Okay? You will see it in 2 seconds. And essentially what we'll implement is your idea of having 2 states. Okay? Or 3 states or 4 states. Okay? So far, I would suggest that if you have time this afternoon, you just get acquainted with the density matrix in this simple situation, so that tomorrow will complicate our life. Okay? So I'll see you tomorrow at 11. Okay? Oh, first we